And I'm supposed to say this. This talk supported by AWM and NSF. It's a requirement, so I can get reimbursement. Are we recording this?
Yes.
Anyway.
You're under record.
So, all right. So first, some part of this talk will be similar to Thomas' talk, but different flavor. Hopefully, you enjoying this. All right, hold on. Oh, and now it work. Let me try this way. Technical difficulty. Right. Oh, okay. So let me do this way instead. So what is vertex operator algebra? First, we're gonna start with vertex algebra. So very analogous to what Thomas said. So you start with vector space. It doesn't have to be z-graded or anything, just vector space, okay? And it's come with operator y. You can see because yeah, I'll have pointer instead. All right, and you have to have key ingredient, which is our vacuum space. And what's an important thing that Thomas mentioned this morning is locality, and this locality actually equivalent to this what's so-called Jacobi identity. All right, and another ingredient that I need is the following: this operator D, okay, that define on this vector space V in the following way. So D of V is V negative 2 x on 1, but V negative 2 x is just the mode of V. All right, so from here, when you see this Jacobi identity, first question is, what is this? And what is good for? All right, so first, I'm going to rewrite it in terms of power series. So when we're comparing coefficients and everything, this is what we got. What's nice about this is the following. All right. So if you let R be 0, this is what we get, which is what's so-called commutative formula, which resemble to the algebra, as you can see. Next, if you take P to be 0, and you get what's so-called associativity formula. All right. So if we assume that the first equation holds, which means that the mode for vector u and vector v, if u and v equal to 0 for n sufficiently large, in fact, the Jacobi identity is equivalent to these two formula, which are commutative formula and associative formula. All right. So what, with this in mind, what is actually telling us is the following. All right. So first, you start with just C-graded. All right. When you talk about C-graded vertex algebra, we're not even going to talk about vertex operator algebra yet, just vertex algebra. So let's say you have Z-graded, integer grading. Okay. So these vectors, this vertex algebra is called C-graded vertex algebra. If it satisfies several conditions, first thing first, the vacuum vectors, which is important ingredient, have to be in V0. Moreover, for any vector u in Vk, okay, and for any integer m, okay, um will act on this homogeneous subspace Vn in this way, and for n-graded vertex algebra is defined analogously. All right, so now the point is, with the Jacobi identity, what is the key ingredient or hidden message that we did not see in the original definition? So now if we focus our attention for the case when V is n-graded vertex algebra, the point is, with suitable identification, precisely when you let R and Q be -1, it's turned out that your bottom level, okay, V0, turned out to be a commutative associative algebra. And if you let P and Q be 0, turn out that V1 is a Leibniz algebra. So this vertex algebra, okay, there are, for each homogeneous subspace, especially V0 and V1, it's hidden like bunch of nice ingredient that you can cook up and actually create a new vertex operator and vertex algebra. And that's a hidden message that will play important roles later on. Now, for many talks, okay, we focus on a particular case when V0 is one-dimensional. Remember that the vacuum vector is in V0, so when it's one-dimensional, so it just means that V0 is generated by the vacuum vector. So for this case, it's turned out that V1 turned out to be Lie algebra. So it shouldn't be a surprise that why Lie algebra is always pop up in the study of vertex algebra. And actually, how it works is the other way around, right? You start with study, when you study the moonshot construction, you have SL2, you have Lie algebra, you construct a phi Lie algebra, and later on, the definition of vertex algebra pop up. But you can see it's a tangle of a web of information that's embedded in one infinite dimensional vector space. All right. Now let's see. Okay, so first example. All right. Give me 1 minute. Apparently, I get disconnected because I changed the page, but it doesn't work. Right. So, what is our part code? Right. Sorry. So, this will take an hour for sure. I was planning to give 50-minute talk, but I'll probably have to log in many times. So that will fulfill my 10 more minutes. XJ, 6C. Okay. Sorry. All right, hopefully my Zoom is working. Is it connecting? No.
Yeah,
That is yeah. All right. So, all right. Click here to X. Let me go to my Zoom again. Delete that.
You want to change the computer?
That's fine. If it's
Yes,
yeah.
Yeah.
Yes, it's like your slides.
Pardon?
Yes, your slides on his laptop, and you can. It is more stable.
Okay. His laptop is stable. Do you have my file?
Make it stable, yeah.
All right. Yeah. Oh, okay. So sure. Let's. All right.
Okay, if you want.
Let me try maybe to download it first and
Right.
because
Oh yes, you have my file. Awesome. All right. All right. So at least I did something, right? I sent my PowerPoint.
Yeah, you can find your slides on the website, by the way. Everybody can on this.
All right.
still.
Now I forgot what I have to say. All right. So, right, we're gonna give example. All right. So the first example that you saw this morning, okay, is about SL2, but the construction is very analogous to what's happening done in Thomas' talk. So you start with not even simple, just start with finite dimensional Lie algebra with a symmetric invariance bilinear form. And next you construct a phi Lie algebra, that's the usual thing, and define it with the following bracket. The point is, the point is you can decompose this phi Lie algebra G hat into 3 pieces, okay, which define in the following way. All right, now the thing is, all right, so you start with one-dimensional trivial G modules, okay, and then you extend this vector space to be a module for, I forgot the hat, apologize, G hat plus and G hat 0 module by letting G hat plus annihilate V0, okay? And K gonna act as scalar, which we call level. So in this case, we set B, which is gonna be our vertex algebra in the following way, which is exactly what has been done in the previous talk. Now by setting one of the vacuum vector in this way, and operator D, which is your L-1 in the future, in the following way, then turn out that this is an example of F5 vertex algebra. The thing is, I need to create a bunch of ingredients to be able to proceed to the next, to the topics I want to discuss. All right, now, this is for any finite dimensional Lie algebra, right? Now, even let H be an abelian Lie algebra, all right, with dimension L, and this abelian Lie algebra equipped with the non-degenerate symmetric bilinear form, okay? So for that, this specific type is, of course, a vertex algebra again, but for this specific type, we call Heisenberg vertex algebra. All right, so let's see. So with this in mind, what makes vertex algebra to become vertex operator algebra? Of course, we need Vertex algebra, right? So, so this is covered a warm-up. So for vertex algebra to be vertex operator algebra, of course, so besides vacuum vectors, you're gonna have to have another vector which we call conformal vector or Vertex vector. All right, which the action we define in this way. So for vertex algebra to be vertex operator algebra, you need this vertex algebra to be a module of Vertex algebra, okay? And this C, all right, so when you have Vertex algebra, it's come with C here, this C, okay? And this C will act as scalar, which we'll call central charge, all right? What else? L0 have to act semi-simply on this vertex algebra B. And the requirement is the dimension of each homogeneous subspace have to be finite dimensional. All right. And then we have to identify D, which L-1. All right. So with that, okay. So many of you are already familiar with this. So I'm just go through this quickly. So
actually, I should clarify that all the probabilists are not familiar at all with this.
Oh, okay. Sorry.
It's good
Okay.
not to go too fast and maybe.
Okay. That's good. That's good. Thank you for letting me know. All right. So let's go back to Heisenberg. All right. So ingredient is abelian Lie algebra with non-degenerate symmetric bilinear form. All right. To construct a conformal vector or Vertex vector. Okay. First thing first, you take autonomous basis of H, which we define in this way, okay? And it's turned out that if you define your conformal vector in this way, okay, omega in this way, it's turned out that this vector gonna become our conformal vector with this central charge L, which is the dimension of this abelian Lie algebra. Okay, now I want to mention for this case, okay, which kind of irrelevant for this talk for now, but it's good for future talk for someone else. This conformal vector is just one of the choice. There are actually infinitely many more. So this is the one that I will use for this talk, okay? Okay, now, so you have this Heisenberg algebra. What else that we have?
These, for instance, can be like the W theories.
Yeah. Exactly.
Is there a reason why you doesn't have to be just L?
Oh.
By the
For this one, because it's compatible with what I'm going to do next. But in general, it doesn't have to be. You can, like, for instance, you can have like omega with this one and minus, pick any elements in a weight one space. So pick any elements in a abelian Lie algebra, and then you can do something like this. And this is gonna create another Barrasso element, Barrasso vector or conformal vectors for you as well. So there are many choices. This is just something that I just pick it up. So it's go along with my talk, that's all, okay? And I'm sure that in other talks that will be this type of example pop up. Actually, in this talk, there will be something similar to this pop up, which I'll point out. Okay, now let's direct our attention to when I talk about, start with Lie algebra, equipped with symmetric non-degenerate bilinear form, and then you can construct a vertex algebra. Now we're gonna look at a specific type, which is a type that G is a finite dimensional simple Lie algebra equipped with scaling form, which is what Thomas talked this morning about when G is SL2. Of course, for this case, it turned out that so you start with G, and you find, because you have a non-degenerate bilinear form, so you find an orthonormal basis for G, defined this way, okay? And you set omega to be this. This is going to be your conformal vectors. And it's turned out that with this conformal vector, we're going to be able to produce vertex operator algebra and come with this central charge, which plays an important role later on. And one more time, this is just one of the choices. You can also do it this way as well. Let's do some changes. But this one, for this case, H have to have some kind of special property, okay, which I don't want to go in. But all right, so now, okay.
Sorry, I mean, this looks like what physicists would call the Sugarawa construction.
Exactly.
I thought in the Sugarawa construction you had some non-trivial prefactor in omega, like 1/2 times H hat plus L, something like that.
You are right, and I forgot to put that in. It's kind of like this. You're right. I forgot to put that in. I apologize, but very good. Thank you. Yeah, there is a typo there. Thank you. All right. So now, this one is vertex operator algebra. Is a universal one. But okay, let's assume that the dimension of L is, let's see. So L is the level. All right. So let's say that if our vectors our numbers satisfy this property, and then we're gonna have a unique maximal submodulus. And in this case, when you quotient this vertex algebra with this ideal, it's turned out to be a simple vertex operator algebra. When I talk about simple vertex operator algebra, so it's mean that no other ideals, no ideal besides zero in itself. Okay. All right. So now next one, which is the last one. All right. So with that, so you have Heisenberg VOA, you have a phi VOA, which is nice. And the next one that I need for my ingredient is vertex operator algebra associated with even lattice. Right. When I talk about even lattice, so you start with for this talk, okay? In general, it doesn't have to be positive definite, but all right. But for vertex operator algebra, I would like to be positive definite even lattice with non-degenerate symmetric bilinear form, okay? And with that, you can construct abelian Lie algebra. That's H defined this way, okay? And you expand this bilinear form to H, okay? So now we're gonna define VL in this way. And it's turned out that VL is a vertex operator algebra that have Heisenberg vertex operator algebra sit inside, okay? And the conformal vector is actually derived from going to be the same one as the one is for Heisenberg, which is this, okay? And the central chart for the Vertex algebra will be the dimension or the rank of the lattice. Okay, so with this, why we need to know all this vertex operator algebras? Because first thing first, I'm going to start talking about rational VOA, and then you can see that something. All right, I make connection with irrational later. All right, so there are many types of modules. When I'm talk about modules in general, okay, which we usually call weak modules. So for weak module, it have exact same definition as vertex algebra, vertex algebra. But what we're gonna focus on is what's so-called admissible module and ordinary module. So for an admissible weak module, it's just a weak module that satisfies the following condition. First, it has to be integrated, and it has to satisfy this condition as well. So Vm will act on each homogeneous subspace Mn in this way. Okay, now, okay, so, and this is gonna relate to rational vertex operator algebra later. Now, what else, what other type of module, which gonna connect to an admissible module in a minute. So an ordinary V module is just a big V module with secret that induced by an action of L0, meaning each homogeneous subspace M mu is just a set of eigenspace with respect to eigenvalues mu. And we have an additional requirement that the dimension of each homogeneous subspace have to be finite, plus this one extra condition, okay? Now, so from here, okay, now I can talk about rational VOA first. So when you talk about rational vertex operator algebra, it just means each admissible V module is completely reducible, which means that it is the direct sum of admissible modules, which is nice. Do we have example of rational vertex operator algebra? Of course we do. Oh, all right. So the first one is the lattice VOA. The second one is F5 vertex operator algebra with the condition that K is a positive integer. All right. So it's turned out, what is the connection between admissible and ordinary modules? It's turned out that is what's shown by Dong, Lee, and Mason, that if V is rational, then in fact, first of all, it means that V has finitely many indecurrent simple admissible modules. And all those admissible, simple admissible modules turn out to be ordinary one. All right. So, which is good. Because with that, okay, with this information, it's gonna come back and tell us, give us more information later. Okay, just remember that you have rational VOA, so it means you have finitely many simple modules. Okay, and every modules can be rewritten as the direct sum of simple modules. Okay, now.
In admissible, do you assume L0 is diagonal or not necessarily?
So, all right. So for admissible, it doesn't have to be diagonal.
Doesn't have to be. Okay.
Right, but for like simple, yes,
no, for simple.
Right. Okay. So now, all right. So I need one more C2 condition. All right. So this one, so the C2V is defined as a set of all linear combination of U minus 2V. And we say that we satisfy the C2 condition if the dimension of V mod C2V is finite dimensional. I should tell you this space is nice in the sense that it's actually a Poisson algebra. What else? This bizarre condition actually tell you how many simple module it has, that vertex operator algebra has. Meaning, if your vertex operator algebra satisfies C2 condition, it tell you that you have finitely many simple modules. It's regardless your vertex algebra is rational or irrational, doesn't matter. As long as it satisfies C2 condition. So it's implied that your vertex algebra has finitely many irreducible modules, and that is nice, and it's payroll later on. So now let's go back and talk about simple modules. So let's say for each simple modules, okay, because it's simple. So you can actually rewrite the grading and rewrite them in this way. All right. The point is, I want to point out that that is especially nice information or this number, which we call this complex number, which we call conformal weight. All right. So with that, all right. So now, so you have a bunch of ingredients mixing together, but now, if you have rational vertex operator algebra that satisfies C2 condition, it seems redundant in the sense that when V is rational, right? And then you already know that there are finitely many modules, but it's necessary to add this C2 condition in to be able to show the following. All right, so it's proved by Dongley and Mason that you have rational vertex operator algebra that satisfies C2 condition. Then indeed, the central chart that come from Russell algebra, and all these conformal weight of each simple modules are rational numbers. So from here, the important ingredients of all this, of those theorems, which and then much more later, is actually come from modular form property. So if you have rational vertex operator algebra, of course, let's say it's come with all these simple modules, right? And for each simple modules, right? So, and for each homogeneous vector, let's call U, you can define trace function in this way, where all U is just U with U minus 1. So the point is preserve the grading of each homogeneous subspace. All right, now, okay. Now I need, by changing the coordinate system from sphere coordinate to be a tube, by rewrite the action of phi in a different way, in this way, it's turned out that something nice happened, and it's proved by Ju in the 90s that, all right, this function, all right, are homomorphic on the upper half plane. Moreover, it satisfies these 9 modular form properties. And actually, this is important ingredient for us to be able to prove many interesting theorems like the previous one. What else? Okay, so with that, actually, we can tell you more about many algebraic structures that sit inside the Lie algebra V1, if your vertex algebra is nice enough. So now when you start with vertex operator algebra V, and this vertex operator algebra is said to be CFT type, if it had to be non-negative integer graded, all right, and your bottom level start with is one-dimensional, dimension of V0 is 1. So it's of this form. So this is what we call vertex operator algebra of CFT type. Okay, now when you have something like this, why this is neat? Because, right, if you start with this vertex operator algebra of CFT type, all right, we say that V is strong CFT type if, right, so right now, so you have, right, V0 plus V1 and so on. The point is, if L1 acts on V1, annihilate V1, so the dimension of, so this one, okay, first of all, it lives inside, is a subset of V0. So if the dimension of these, if L1 annihilate V1, this is a good thing. Why this is a good thing? Because actually, this quotient space tell you how many non-degenerate bilinear, invariant bilinear form that we have for vertex operator algebra. So for this case, is the case that V0 has is one-dimensional and L1 acts on V1 as 0. So it's tell you that the dimension of this quotient space is 1. What is neat about this? When this happens, it's tell you that in fact there is one unique non-degenerate invariant bilinear form, but this strong CFT type. So that's why it's quite crucial for us to have this nice property. All right, so with that, oh, I already said it. Okay, this proved by High-Shingley. All right, if you have simple vertex operator algebra, we satisfy the above condition, this one, then you've got a non-degenerate invariant bilinear form. Okay, now, I know I speak fast, I apologize. So with that, what's so neat about it? Well, okay. So what does this mean is, if you have, so you have a unique non-degenerate bilinear form, right? So if you have vertex operator algebra of CFT type, it just means that your vertex operator algebra is self-dual. So it means that your contract gradient modules we had, we check, and now can't speak English anymore. All right, so it's isomorphic to a joint module V. All right, and it satisfies nice additional, there are a bunch of nice additional properties. But the point is, now if you focus on V1, remember that if you have vertex operator algebra of CFT type, V1 become a Lie algebra. So what's so nice about having non-degenerate bilinear invariant bilinear form? By the way, if you have a non-degenerate invariant bilinear form, what's happening is, if you have two different homogeneous subspace, and N is not N, okay? So it's turned out that they are orthogonal to each other. So, which means that for each homogeneous subspace Bn, this bilinear form become non-degenerate on each homogeneous subspace as well, which is neat. Because from here, so when you have Lie algebra, which is on V1, and you have this nice property, so your Lie algebra V1 actually have a non-degenerate bilinear form if your vertex operator algebra is a strong CFT type, okay? Which is good. Now, keep that in mind because we need to define one more thing. All right, so strong CFT type is good. It means that V is dual to, is self-dual. Now, what even better is what's so-called strongly rational. So it's for vertex operator algebra to be strongly rational. So first thing first, it has to be strong CFT type, satisfy C2 condition, and then rational. One thing I should tell you, and I forgot, sorry. So if you combine these two conditions, all right, rational plus C2 condition, it's turned out that you can show that every weak modules, meaning that it doesn't have to have any grading, in fact, can be rewritten as a direct sum of simple modules, which is nice. So this combine these two conditions will give you even better result. All right.
Sorry, just does a unitary rational model is
it's sitting
is
there.
this?
Yeah, exactly. Very good. Yeah. Okay, now, when you have strongly rational vertex operator algebra, what even better is turn out that your Lie algebra V1 is reductive, and every V module is completely reducible V1 module. So you kind of have a nice strong structure and a lot of information when you have rational VOA. All right, strongly rational VOA. Okay. All right. So with that, okay. So now let's see what can we do with the information that we have in hand. So before we talk about rational, just focus on the case. This V is a simple vertex operator algebra, satisfies C2 condition, doesn't have to be rational, remember, of strong CFT type, meaning it's self-dual. So let's say that for this case, okay, let's say the V1, which is your Lie algebra, all right, contain a simple Lie algebra G, all right, of level K. Then for this case, okay, you can, if you restrict ourselves, so vertex operator algebra is self-dual, right? So you have bilinear form. If you restrict that bilinear form, okay, that bilinear form is non-degenerate. But when you restrict to G, one can show that this bilinear form is non-degenerate. Moreover, okay, if you have vertex operator that subalgebra that generate by G, is turned out to be a nice rational F5 VOA. Okay, K is positive. And V is actually integrable G hat modules, meaning that for this case, you can describe the algebra of vertex algebra beautifully. All right, which is good. So that's why rational is nice and neat, and you get a lot of information, except the case if you cannot, if V1 is 0, so we are in trouble. That is harder problem. All right. Now, if you have
So here, V is not rational.
this is rational. This one, the top one, doesn't have to be rational.
The first one is not rational.
Not that, just simple, just simple. All right, so we have simple VOA, good thing happened.
Yeah.
All right, so now if you have strongly rational VOA, and let's say that you have, let's see, subalgebra, I should say abelian, apologize, abelian subalgebra of rank L, okay? Such that the restriction of this bilinear form, because it's strongly rational, so it's come with a nice bilinear form. So if you restrict to H, okay, it's still non-degenerate. It's turned out that for this case, under a nice assumption, we need to impose some condition. And it's turned out that if this nice condition happen, there will be a lattice VOA. So you're gonna be able to find a positive definite even lattice, all right, that you can use to create a VOA that sit inside this vertex operator algebra. So you can see that when you have a rational VOA, okay, well, strongly rational VOA, and then a lot of good things happen in the sense that you have a rational F5 VOA sit inside, and you also have lattice VOA sit inside, and they're both rational. So you can actually describe the algebraic structure of this abstract vertex algebra by read off information from rational F5 VOA and lattice VOA, which is good. Now, okay, so with that, this is good. This is CFT type. So which is for us is the case when V0 is one-dimensional. So the question is, what's happened if the dimension of V0 is no longer one-dimensional? Can we say something? Do we have nice algebraic structure, or what's going on? Because in some sense, for that case, your bottom level V0 is commutative associative algebra. That's interesting. V1 is a left Leibniz algebra, interesting as well. So what are those algebraic? How those algebras play a role in the study of n-graded vertex algebra for the case when the dimension of V0 is greater than or equal to 2. All right, so for this case, something neat happen. All right, so I already mentioned this. So for this, actually, there are many easy tools for us to be able to use on. First thing first, actually they define for vertex operator. Dong and Mason define this for vertex operator algebra, but I'm just gonna take the word operator out. So you start with vertex algebra. Your vertex algebra is local if it has unique maximal ideal. Now, why this is good thing? Because it tells you a lot of information. All right, so it's shown by Dong and Mason that, all right, you have n-graded vertex algebra where the dimension of the bottom one, dimension of V0 is greater than the 2. In fact, V is local, even only if V is indecomposable, even only if V0 is local algebra. Meaning, if you want to study the whole structure of vertex algebra, all you need to do is look at the bottom level, what's going on. If V0 is local algebra, that's nice, because it tells you that your vertex algebra is indecomposable immediately. All right, so, okay, now, so let's see. So what can we say about this type? And I'm going to connect back to CFT type later. So when you look at Leibniz algebra, okay, so if it's what's shown by Barnes that every finite dimensional Lie algebra has a Levy decomposition, meaning it's a direct sum of simple, semi-simple one plus the radical one, okay? So that is mean for Levy decomposition. Now, so Mason and I showed the following. You start with n-graded vertex algebra, simple, self-dual, okay? So we need to satisfy C2 condition, okay? So for this case, and our semi-simple, the algebra here is not 0. It's turned out that this vertex operator algebra, this n-graded vertex operator algebra, is just a module of this rational vertex algebra. So it's kind of like, as long as you have simple algebra with nice bilinear form, this one is self-dual, you still can like get a lot of information on the algebraic structure of V by study or by think of it as a module or a representation of rational, this F5 VOA, okay? Now the question is, what happened if the solvable one or the semi-simple one no longer exists, right? So V1 is the solvable, left Leibniz algebra. What can we say about it? And actually, the question is, what this have to do with CFT type? Is this useful? Well, first thing first, let's see. Do we have example of n-graded vertex operator algebra such that V1 is solvable, left Leibniz algebra? All right, this one you have seen it from the previous talk and this talk. All right, so you start with SL2. All right, so this is a rational VOA, right? Now, and this KK is a positive integer. All right, now the thing is, if you change your conformal vector a little bit, so your SL2 generated by E, F, and H, all right, the usual one. And I shift the original conformal vector that I defined previously by a half times H minus 2, 1. It's turned out that you change the grading of your F5, rational F5 VOA. This one is what CFT. But if you change the grading to be of this form, it's turned out to be n-graded vertex operator algebra. Remember that when you start with this one, all right, your V1 is a simple Lie algebra, but it's turned out that for this case, if you change the grading a bit, your V1 turned out to be a solvable Lie algebra. But the point here is, your V0 have a very nice commutative associative algebra structure like this. Okay, so now why this is helpful? Because you see that this is an example that you have vertex operator algebra of CFT type, and you can't tell whether it's simple or not. It's too hard to calculate. One thing you can do is you shift the conformal vector a bit and change the grading. It's probably work for some, but not for all. But with that, the thing is, you change your conformal vector and then you convert your CFT type vertex operator algebra to be n-graded vertex algebra. And you have the previous two that say that, all right, all you need to do is look at the bottom level. If your V0 is local, and it tells you immediately that your vertex algebra become indecomposable. So this become handy just by changing conformal, shift your conformal vector a bit. Okay.
So saying the zero weight space is a non-semi-simple algebra?
So this one, right, so zero weight space gonna look like this.
It's non-semi-simple algebra.
This one is a local algebra. It's
Yeah, it has a union by X.
right.
Why is it so? Why is it of this form?
Pardon?
Why is it of this form? Why is it?
Why? Because when you change the your grading, right? And the point is your L0, the new one,
Yeah.
is going to be like the old one minus, I think, half H0.
No.
So when you change the grading, and then actually all the E move down and all the F move up. And so it's turned out so you can change the shape is like a dome. You change the shape and then you be able to get answer a lot of questions. All right. So, okay. Now, in this case, so do we have an easy tool to determine whether V1 is a solvable Lie algebra? And can we use that to study rational n-graded vertex operator algebra that satisfies C2 condition that's not CFT type? All right. Turn out that there is an easy tool. And I'll tell you about a rational case later. If I'm not run out of time, right? I still have some time. All right. So I have to do a bunch of ingredients. So this page is all the ingredient I need. So this will be useful for V0, our commutative associative algebra that on the bottom level. So if you have a ring, let's call A, it's Artinian ring. So the so-called is just the sum of all modules of A. All right. So it turned out that in fact you have Artinian ring. So the so-called of A is just annihilators of the Jacobson radical. Okay, here's come the point. Now you can see the word brokering. So if you have a commutative associative algebra, I should read off what it's wrote, commutative Artinian local ring with a unique maximal ideal M. So it's turned out, so M is our Jacobson radical. So the so-called gonna annihilate this maximal ideal M. All right, why this is good? Because, so this special type ring, which is Gorenstein, okay? This Gorenstein ring, if the so-called A is a simple A modulus, so we call this ring A Gorenstein. What neat about Gorenstein ring is because it comes with nice bilinear form. So you start with an Artinian algebra that is finite dimensional, and let's assume that A is a graded algebra of this form. Okay, so we say that A is a concurrent duality algebra, meaning have a nice bilinear form, if and only if A is Gorenstein. Okay, so the point is, if A is Gorenstein and the so-called is AD, which will play important role later. All right, now, the thing is, you have n-graded vertex algebra, the your V0 is Greenstein, which means it's come with a nice bilinear form, all right, with a unique maximal ideal n, and it satisfies this property, which actually is a key, important key. But the point is, which I'll explain to you later. If every subalgebra of left Leibniz algebra, V1, is closed under this maximal ideal of cognitive associative algebra, okay, then it's turned out that V1 is a solvable left Leibniz algebra. So what does this tell you? Actually,
What do you mean by closed under M?
pardon?
What do you mean by closed under M?
Oh, because closed under M means, so let's say A is in M, but M is a subset of V0, right? An ideal sit inside V0. So it just means that A minus 1 acts on U. So if U is every subalgebra, all right, U is in V1.
And so every V1 is a V0 module or what?
Yeah, so V1 is always V0
V0
module.
module.
Right, so
I
if
was
closed
about to
under,
be closed under the action of M.
right, so it's a module of, so V0 is a commutative associative algebra, right?
Yes.
So and V1 is a module, but it's not really a module as commutative associative algebra, but definitely V0 acts on V1 and send it back to V1 under -1 mode. Oh, my dentist called. I'm sorry. Okay, so now, so what's happening here is actually knowing the structure of V0 can describe the algebraic structure of your left Leibniz algebra. It's turned out to be solvable, which is bizarre, but it's happened. All right, so now with this, okay, so with this, a lot of things going on, but the point is, you have n-graded vertex. I know that I call semi-conformal vertex algebra, but think of it just like vertex algebra for now. Identify semi-conformal. With V0 is a graded algebra that is a Greenstein ring. Okay. With this condition, which I'll review later, what does this mean? All right. So when you have Greenstein ring, so it means you come with this nice bilinear form, non-degenerate bilinear form. All right. Now, remember that I can find an element in this unique maximal ideal that can generate the circle. I'm going to call this element T. And the point is, with this, okay, the point is I can construct, so B has a non-B, which is a map, a non-degenerate bilinear form for this Greenstein algebra V0, right? So with this, first thing that comes with these properties, B of the vacuum with T is not 0. So when you have a non-degenerate bilinear form on V0, the point is you can lift this up and construct an invariant bilinear map for vertex algebra, which satisfies this condition. Okay, now I think I'm running out of time, but the thing is, the point is all of this is I can be able to, with this, we're gonna be able to construct a lattice later on. So on the left, so we have a map that's cosine from V1 to CT, and I'm gonna let M be the kernel of this map.
Sorry, you're too fast.
Okay.
Still. So this bilinear form you define on V?
Right. This. So
Or
you
is it
start with
this one,
B.
or-
So this is B.
B, okay.
We have B, right?
Yeah.
So this is from Greenstein. And with this B, you can use it to define an invariant bilinear form on vertex algebra. B this way. So this depend on B. So you need to get the bilinear form on V0 first, and then you can use it to construct invariant bilinear form on vertex algebra. So everything that you see is color depend on this, on our commutative associative algebra V0. So, okay. And by the way, tell me, okay, I'll go too fast. And then you can, and one more thing. So this one is a circle, and this circle turned out to be a module of this left line is algebra B1. Okay, so you can define.
But B is unique.
Pardon?
B is unique.
B is
With your conditions.
yeah,
With
yes,
maximal
yes,
ideal
I
and
think
so
so. Yeah. All right. Okay, so with that, the point is, so if you have an integrated vertex algebra that V0 is current styling, so you can find one nice element in V0 that annihilate this maximal ideal.
So it's in the
Yeah.
circle.
Right, so in this case, the point is, with that, we can use that information to find a generator for Heisenberg vertex operator algebra that sit inside V. So this integrated vertex operator, this integrated semi-conformal vertex algebra is actually a module of Heisenberg. Just one, but we can expand more. This H is not unique, there are more choices. It depends. All right, so with that, okay, this is exact same thing I said in the previous. I just want to point out that, so this is you can find elements in V1 that really form a abelian Lie algebra with all this nice Heisenberg property. Okay, so, all right. So in this case, let's see. All right, so now the thing is the hard part about integrated that's not vertex operator algebra, that's not CFT type is because it doesn't come with nice bilinear form. It doesn't mean that it does not necessarily non-degenerate. So to do that, that's why I had to go over to V0 to get some nice current styling to lift it up to be to have a nice bilinear form on V0 and lift it up to be a nice bilinear form on VOA. But so now with this map, this is a bilinear map, because remember that so when you can have an action from V1 to V1, but it's go to V0, all right, by sending U and V to U1V. But the point here is in V0, which is a commutative associative algebra. Our vertex algebra is no longer CFT type. So which means that this is not V1. This is not necessarily bilinear form. So to do that, we have to do a lot of restriction. And this is how we do it. So given any element U and V in V1, we can define this bilinear map in this way instead. So, and okay, so it's turned out that, all right, I'm sorry, I know go fast. So the point is, so when you have V1, you can decompose it into two parts. The radical part with respect to this bilinear form and U. And this U is, the restriction of this bilinear form is non-degenerate. And the point of all this is because so we can have nice Heisenberg. So if you have a collection of all, let M be a collection of all left Leibniz algebra W that's contained in U, and the restriction of this bilinear form to W is non-degenerate. Then, okay, we know for sure that this M is not zero because it's contained this abelian Lie algebra. So we go do all that hard work to ensure that we have something in this collection. All right, and I'm gonna let this cursive M to be maximal left Leibniz algebra that contained it in M. Okay, so with that, once again, so that's why so you start with this solvable Lie algebra, all right, such that L1M equal to 0, it's turned out that L1M is reductive. Indeed, it's abelian. and the action of M on each simple V module is completely reducible. So at least for this case, you can describe the algebraic structure of this integrated vertex, a module of this integrated vertex algebra in terms of Heisenberg modules. All right, now in this, indeed, all right, so this word, so you can have sub-vertex algebra generated by M, and this is Heisenberg. All right, here comes the point. The point is, so you have a nice rational integrated vertex algebra. All right, it's turned out that satisfies C2 condition and all the condition that we had previously. It's turned out that there is a lattice sit inside this rational integrated vertex algebra. I think I'm over time. All right, so, but the thing is, I can already prove that it's non-negative definite, which drives me crazy. I'm trying to improve it to be positive definite, but there are some lattice VOA for sure sit inside. All right. Now the thing is, okay, so you see something nice about rational, but the question is, this is the last one. How can we differentiate between indecomposable non-simple module and simple, indecomposable non-simple vertex algebra from simple vertex algebra? You see that if you know this, thing come handy. Do we have an easy two? And the answer actually yes. All right, so you have integrated vertex algebra. First thing first, this seems hard to try to determine the algebraic structure, but one thing you already needed, look at V0, right? If you have a map, D from V0 to the V1, defined this way. In fact, if the kernel of this map, which you see all the time that in my talk, then V0 is local algebra. That's it. This is all you need. Make sure the kernel of this map is one-dimensional, generated by the vacuum. Then your V0 is local. Why this is good? Because if V0 is local, so it means your vertex algebra V is indecomposable, regardless of what conformal vectors you use. Now, so that's good because, all right, so we know this. Now the thing is, so you know that easy to determine whether your vertex algebra is indecomposable or not. You just look at your commutative associative algebra on the bottom level. Now, how do you differentiate between indecomposable, non-simple, and simple one? Actually, that is not bad either, because all you need to do is look at this map, all right? So you can create a map from V1 times V1 to V0, which is this one that I described before. Now, the thing is, the point is, so when you have this map, right? So you can define radical in this way. And this radical actually is a Lie algebra. If your vertex algebra is generated by V0 and V1, meaning generated by commutative associative algebra, and left Leibniz algebra. In fact, if the ideal generated by this radical is not zero, so your vertex algebra is non-simple immediately. So with that, so you can see that it's not too bad. All you need to do is play around with V0 and V1 and see what's happened, and you can tell a lot about the algebraic structure of vertex algebra V. Now, I want to show you something that I found is bizarre but interesting. So, before that, when you have CFT type, if you have simple Lie algebra, you can construct simple VOA and rational one. Now, if we do this again, you start with a simple left Leibniz algebra. All right, we satisfy this condition. It's turned out that we can construct a new integrated vertex algebra satisfy C2 condition, which is neat. But this vertex algebra is no longer simple. It's indecomposable, non-simple. The point is, if you quotient it out by its maximal ideal, it's go back to the CFT type. But at the end of the day, I'm going to stop here. You can construct easily infinite dimension or construct integrated vertex algebra easily from simple left Leibniz algebra And this vertex algebra satisfies C2 condition, and it's not simple, but indecomposable. So I'm gonna stop here. Thank you for your patience.
There are questions? Speaker? So there are many questions. I have a question. But all these algebras, what can they tell us about representations? I mean, like we understand that they represent. I mean, is there some relation between the representations of all these algebras appearing at different levels with representation?
Right. So I'm not going that far yet. So far for the rational one, we can tell by look at the lattice VOA and all that, because the
No, for non-rational when it's not semi-simple.
Right.
For non-rational.
For non-rational is one thing. All right. So for this case, it's actually there is a rational F5 VOA sit inside this one. So it means that you can also study module in terms of rational F5 VOA. But it's strange because in a sense that, like for example, this one, if your B, it generates your G here is SL2. So your word, I can write down explicitly, but it's A. But the point is this VB is going to be direct sum of two simple modules of F5 VOA. But when you add them together, you get VB, but it's become non-simple. But it's still like a long way to go. But that's a very good question. I still don't have a clear path how to do this yet in general.
Or maybe a simpler question, I don't know, like I would like to understand if my VOA is not simple. I mean, you provide sort of criteria, and I would like to can understand sort of chain of ideals, structure of VOA itself in terms of ideals.
Yes, actually, that is my work with
length. Say.
Right.
Can you say what is length, maximal length?
Well, I can say what the module actually, because there is another work with me and Hai Xing Li that I didn't put it in here. So what's happening is, so this one, what's so-called vertex algebra here, actually give you a description. So the modules of this vertex algebra going to be corresponding to the module of a so-called vertex algebra. So I can answer some by just like study that the module of that vertex algebra and induce it up. So you get a collection of modules for this vertex algebra. But the thing is, I'm not sure that I captured all. And that I'm not sure that I can capture all the information. So I can't give you only partial answer.
Thank you. There are no more questions. Thank the speaker. You all, or most of you, at happy hour.